Yeah, welcome back to recurrence relation part 2. In part 1, we have studied what is a recurrence relation, what is the types of recurrence relation, and how to find the solution of homogeneous linear recurrence relation. In our syllabus, only linear recurrence relation are given, and we will see the solutions of homogeneous and non-homogeneous both. In previous lecture, we have already covered the solution of homogeneous recurrence relation. Today, we will study the solution of non-homogeneous recurrence relation. Okay, let's see. Solution of non-homogeneous recurrence relation. So I told you if a recurrence relation is A naught Fn plus A1 Fn minus 1 plus so on AK Fn minus K equal to Gn, and this is called the recurrence relation of order K if A naught and AK both are non-zero, of order K linear recurrence relation of order K. If Gn equal to 0, it become homogeneous linear recurrence relation. And if Gn is non-zero, it is for all n. Non-zero, it is called non-homogeneous linear recurrence relation. So general solution of recurrence relation is defined as homogeneous solution, means solution of corresponding homogeneous part plus particular solution like a differential equation. Particular solution we obtained corresponding to Gn only. This is the solution corresponding to homogeneous part. Homogeneous part. This is corresponding to Gn, corresponding to Gn, and if we substitute it, we get LHS equal to RHS. And if we substitute it, we get LHS equal to 0. Means we substitute in the LHS because Gn is 0, then we get LHS equal to 0. The solution satisfy the homogeneous part, and this satisfy LHS equal to RHS. Now, how to find this particular solution corresponding to this non-zero function Gn? We have certain rules or cases. Case 1. When Gn is of the form of a polynomial of degree m in unknown n. If unknown is k, then we will see the degree in k. I have discussed unknown can be given in m, n, r, k, in any variable. Like Gn is given as k naught plus k1 n plus k2 n square up to so on km n to the power m. This is a polynomial in n of degree m, then km must be non-zero. In this case, we assume the corresponding particular solution in the form of particular solution PS as q naught plus q1 n plus q2 n square and so on qm n to the power m. Here q naught, q1 and qm are unknowns. We have to find these coefficients. With these coefficients q naught, q1, q2. This method is called undetermined coefficient method. Undetermined method of coefficient. We have to find these coefficient. We will assume this is a particular solution and we will substitute in the given recurrence relation, and we after putting the value in the given recurrence relation, LHS will be equal to RHS. Then we will compare both the sides and we will find Q1, Q2, Q0, everything. We have a special remark here. If K1, K2, Km are 0, means Gn is a constant value. Suppose K0. Gn is a constant value K0. Then particular solution will be given as Q0 only, because the rest term we will put 0. So if corresponding to a constant value, particular solution is a constant value. Constant value. But some people confuse. What is the remark 2? Suppose Gn is your only n, then particular solution will not be Q1 n. It will be Q0 plus Q1 n. If it is of degree n 1, then we will take all the term less than equal to degree 1. Less than equal to degree 1. If it is suppose n square, we will take all these three terms Q0 plus Q1 n plus Q2 n square. Less than equal to the degree of the polynomial Gn. Okay? Okay, fine. Suppose Gn is n square, then we will assume particular solution Q0 plus Q1 n plus Q2 n square. Okay? This is case 1. Let's see the case 2. When Gn is of the form Gn polynomial into some value also, K1n plus K2n square plus Kmn to the power m into a to the power n. A to the power n. Okay. The corresponding particular solution of the form will be, Q0 plus Q1n plus Q2n square and so on, Qm n to the power m, a to the power n. Here 2 points are very important. Remark 1. This case 2 is valid if a is not root of characteristic equation. If a is the root of characteristic equation, this form will not be valid. The particular solution form will not be valid. What will be the remark 2 here? If suppose K1, K2, Km are 0, means Gn in the form of K0 a to the power n, then particular solution will be given as Q0 a to the power n. Q0 a to the power n. But what is third point? If Gn is given as suppose n into n square into 5 to the power n, then particular solution degree is 2. So all the term less than degree 2 we will take Q0 plus Q1n plus Q2n square into 5 to the power n. So for this type of example, particular solution will be this. A to the power n will come in the multiply in every case. So here a to the power n is 5 to the power n. So for this term only we have to manage. Case 3. If a is the root of characteristic equation, if a is root of characteristic equation of multiplicity r, suppose a is repeated r times, means r times same root is coming 3 times, 4 times, r can be 3, 4, 5, 2, 1, any value. And Gn is in the form of, and Gn is given as K0 plus K1n plus K2n square plus Km n to the power m, a to the power n. Same case 2, only difference is in the case 2, a is not root of characteristic equation. Here a is the root of characteristic equation. Then particular source is similar, Q0 plus q1n plus q2n square plus qm n to the power m, very good, a to the power n. Only difference is we have to multiply here. We have to multiply here n to the power r. N to the power r. N to the power r. Take some cases. Case 1. If K1, K2 and Km are 0, means Gn in the form of K naught a to the power n, and a is root of characteristic equation. A is root of characteristic equation with multiplicity r time repeated. Then particular solution will be n to the power r q naught a to the power n. Q naught a to the power n. Suppose you have case 2 like this. If Gn in the form of suppose n into 5 to the power n, then can you tell me? And suppose 5 is repeated 2 times. Then can you think the particular solution? Yes, we can think. For n, we will break like case 1. Degree is 1, so less than all the degree 1. Q naught plus Q1 n. Very good. 5 to the power n will come in the multiply. Now 2 times repeated, so n square we will multiply. See carefully. It is degree 1, so all the term less than degree 1. It will be Q naught plus Q1 less than equal. Both we will take. Into 5 to the power n, it will come here, and 2 times, so n square. If 3 times n cube, if 1 time n to the power 1. So this is the way to write the particular solution here. Practice to write the particular solution if any doubt. Let's see some examples. Then your doubt will be clear. Solve sk minus sk minus 1 minus 6sk minus 2 equal to minus 30 given as 0 equal to 20 and s1 equal to minus 5. Let's see the solution. See carefully, k is variable here. K is variable here. So firstly we will solve for homogeneous solution, then we will find particular solution. So associated homogeneous linear recurrence relation is, can you tell me the homogeneous part? Yes, sk minus s k minus 1 minus 6s k minus 2 equal to 0. Or you can write like also this, sk minus 1 minus 6 sk minus 2 equal to 0. Meaning is same. So write the characteristic equation. For writing the characteristic equation, I told you sk can be written as r to the power k form. So r to the power k minus r to the power k minus 1 minus 6 r to the power k minus 2 equal to 0. Divide by r to the power k minus 2, you will get r square minus r minus 6 equal to 0. So r is minus 2 comma 3. So homogeneous solution or solution of homogeneous part is, I told you in the previous lecture, a1 minus 2 to the power k, because you are dealing in k now, plus a2 3 to the power k. Why I am writing k here? Because k is variable. If n is variable, we will write power n. Now our aim to find the particular solution. Particular solution. How to find the particular solution? As we can see that the given equation is sk minus 1 minus 6 sk minus 2 equal to minus 30. So if we compare with right hand side, gk is minus 30 here. Gk, why I am writing gk? Because we have taken gn previously in the variable n, and but given a differential equation or recurrence relation in k, so I am taking gk. And it is a constant value. So like remark of case 1, k naught is given minus 30. The constant value is given minus 30. So in the case of constant value using case 1, we can write the particular solution as q naught. So then, so let particular solution is q naught. If this is a particular solution, because this is a constant value, so particular solution will be constant only. So it will satisfy the given recurrence relation. And after substituting this value, we will get LHS equal to RHS. Substitute. This is a constant. So for every value of K, the value will be Q naught. So for Sk, it will be Q naught. For Sk minus 1, it will be Q naught minus 6. Sk minus 2, it will be Q naught equal to minus 30. So it will be Q naught will be your 5, I think. So this is your particular solution. So general solution will be homogeneous solution plus particular solution. The homogeneous solution was a1 minus 2 to the power k plus a2 3 to the power k. Particular solution is 5. So this is your general solution. Now, if initial boundary conditions are given, these are some boundary conditions are given. So we have to find the value of a1 and a2 also. So this is your general solution for Sk. Okay. Now Sk is given as a1 minus 2 to the power k plus a2 3 to the power k plus 5. Now for S0 is given as 20. So put 20. It will be a1 minus 2 to the power 0 will be 1 only, 3 to the power 0 will be 1 only, a2 plus 5. So a1 plus a2 equal to 15, equation number 2. Call it as second equation, call it as a first equation. And S1 is given you minus 5, so minus 5 equal to a1 minus 2 plus a2 into 3 plus 5. Solve 3 and 2, you will get a1 and a2. I am telling you answer. a1 is 11, a2 is 4. So put a1, a2 in equation 1. So Sk will be 11 minus 2 to the power k plus 4, 3 to the power k plus 5. You can check also the answer. Put k equal to 0, you will get S0 equal to 20. Put k equal to 1, you will get minus 5. So this is the first problem I am discussed. I am giving you similar problem when the right hand side is a constant value for practice. So as a homework problem I am giving you, homework problem is find the general solution of the recurrence relation Fn minus 5 Fn minus 1 plus 6 Fn minus 2 equal to 1. Here I am not providing boundary conditions, so you can write the solution in the terms of unknown a1, a2. Okay, next example I am going to discuss example 2. Now I am going to find only particular solution. Homogeneous solution you can find using the first part lecture. Particular solution of recurrence relation Fn plus 5 Fn minus 1 plus 6 Fn minus 2 equal to 3n square minus 2n plus 1. Now you can see this. The given recurrence relation is in variable n and right hand side is a polynomial of degree 2, 3n square minus 2n plus 1. So using case 1, particular solution will be q naught plus q1n plus q2n square. Use case 1. Now this is a particular solution, so it will satisfy the given recurrence relation. So substitute Fn, it will work as Fn. It will work as Fn. Always remember, it will work as Fn. Work as Fn. Okay. Work as. So it will be q naught plus q1n plus q2n square plus 5 Fn minus 1 q naught plus q1n minus 1 plus q2n minus 1 whole square plus 6 Fn minus 2 q naught plus q1n minus 2 plus q2n minus 2 whole square equal to 3n square minus 2n plus 1. Now we will collect the coefficient of constant n and n square. After collecting the coefficient, we will get 12 q naught minus 17 q1 plus 29 q2 plus 12 q1 minus 34 q2n plus 12 q2n square equal to 3n square minus 2n plus 1. Now after comparing the coefficient, 12 q2 is equal to 3, 12 q1 minus 34 q2 is equal to minus 2, and 12 q naught minus 17 q1 plus 29 q2 equal to 1. Put values here, so you will get q2 equal to 1 by 4. Put q2 here, you will get q1 equal to 13 by 24. Put q1 q2 here, you will get q naught equal to 71 by 288. So particular solution was q naught plus q1n plus q2n square. Put the value of q naught, q1 and q2 here, 71 by 228 plus 13 by 24 and plus 1 by 4 n square. This is particular solution. So I'm giving you a similar problem as a homework. Solve fn minus 7 fn minus 1 plus 10 fn minus 2 equal to 6 plus 8 n. Given boundary conditions are f0 equal to 1 and f1 equal to 2. It is a very important problem. Now let's see another example based on case 2. Find example 3, particular solution of the recurrence relation fn plus fn minus 1 equal to 3n into 2 to the power n. Okay. So this is your polynomial of degree n, degree 1, and this is a to the power n. So it's like case 2. You can see that case 2. It's a polynomial and this is a to the power n. Only it can be case 2 or case 3 also, but we have to check is a 2 is a root of characteristic equation or not. So see the characteristic equation firstly. So associated, I'm going to write the solution. Associated homogeneous linear recurrence relation is fn plus fn minus 1 equal to 0, and its characteristic equation will be r plus 1 equal to 0. You can check it. So r equal to minus 1. So homogeneous solution is a1 minus 1 to the power n. So we can see that 2 is not root of characteristic equation. If this 2 is root of characteristic equation, we will go to case 3. So here particular solution will be, now 2 to the power n will come in the multiply. Only we have to tackle this 3 to the power n. See carefully, students, 3 to the power n, degree is 1. So we will take all the terms of the particular solution of degree less than equal to 1. So q naught plus q1 n. We have to go up to this one. q naught plus q1 n into 2 to the power n. Now if this is a particular solution, it must satisfy. So satisfy this equation. It will play a role of fn here. So fn is q naught plus q1 n 2 to the power n plus fn minus 1 will be q naught plus q1 n minus 1 2 to the power n minus 1 equal to 3 and 2 to the power n. Now again collect the coefficient. You will get here 3 by 2 q naught, you can see, minus 1 by 2 q1 2 to the power n plus collect the coefficient of 2 to the power n and n into 2 to the power n. 3 by 2 q1 n into 2 to the power n equal to 3 into n 2 to the power n. Compare the coefficient. Here n into 2 to the power n has coefficient 3. So 3 by 2 q1 equal to 3, but there is a no coefficient of 2 to the power n, so we can write 0 into 2 to the power n. It means 3 by 2 q naught minus 1 by 2 q1 equal to 0. After solving this, we can see that q1 equal to 2 and q naught equal to 2 by 3. So q1 is equal to 2 and q naught equal to 2 by 3. It means particular solution was q naught plus q1 n 2 to the power n equal to 2 by 3 plus 2n 2 to the power n. So this will be the solution of this problem. Similar problem I am giving you as a homework. an plus 5 an minus 1 plus 6 an minus 2 equal to 42 into 4 to the power n. 42 into 4 to the power n. Next example I am going to solve on based on case 4. Fn minus 2 fn minus 1 equal to 3 into 2 to the power n. Find general solution. Find general solution. So let's see solution. Associated homogeneous linear recurrence relation is Fn minus 2 Fn minus 1 equal to 0. So characteristic equation will be R minus 2 equal to 0. You can see that Fn equal to R to the power n minus 2 R to the power n minus 1 divided by R to the power n minus 1. So R equal to 2. So homogeneous solution will be A1 2 to the power n. Now 2 is root of characteristic equation with multiplicity. Multiplicity means how many times it is repeated? Only one time. And 2 is present here also. So writing particular solution is a difficult job. Now let's see case 3. Case 3 and case 3 remark 1. Remark 1 and it is like remark 2. Gn in the form of constant into a to the power n. And a is a root of characteristic equation. So it's a look like similar problem. Constant is 3 here and 2 to the power n. So particular solution in that case was n to the power r q naught a to the power n. So write in this form only. R is 1 here because it is repeated one time. So n to the power 1. Okay. Q naught. Now next term was a to the power n means same term. 2 to the power n. So q naught n into 2 to the power n will be the particular solution for this problem. Now put this solution, it will play as a role of here an, the first term an. Now substitute in the given recurrence relation, it will be q naught n into 2 to the power n plus 5 into q naught n minus 1 2 to the power n minus 1 plus 6 q naught n minus 2 2 to the power n minus 2 equal to it was for this problem actually Fn equal to Fn minus 2 Fn minus 1. So it will play role of Fn here. So Fn is q naught n into 2 to the power n. So q naught n into 2 to the power n minus 2 Fn minus 1 q naught n minus 1 2 to the power n minus 1 equal to right hand side is 3 into 2 to the power n. Okay. So it will be q naught n into 2 to the power n minus it will be 2 to the power n again q naught n minus q naught 2 to the power n equal to 3 into 2 to the power n. So it will be q naught n into 2 to the power n minus q naught n 2 to the power n plus q naught into 2 to the power n equal to 3 into 2 to the power n. This term is cancelled out. So q naught is equal to 3 here. Q naught is 3 here. So particular solution will be in this case q naught is 3 into n into 2 to the power n. 3 into n into 2 to the power n. So this will be the particular solution for this problem. So I'm taking one more example. If root is twice repeated, suppose example 2 is based on this case only Fn plus 2 minus 4Fn plus 1 plus 4Fn equal to 2 to the power n. Okay. So associated homogeneous linear recurrence relation is Fn plus 2 minus 4Fn plus 1 plus 4Fn equal to 0. So characteristic equation is R square minus 4R plus 4 equal to 0. R equal to 2 comma 2. So it's repeated twice. Okay. Now twice repeated. So homogeneous solution will be a1 plus, now it is n variable, n into a2 2 to the power n. 2 is root of characteristic equation with multiplicity 2. Okay. Now can you write the particular solution here? I am writing here only. Particular solution will be 2 to the power n will be outside, n to the power this value Here I am taking r, so call it as n to the power p. You can change the notation if you want. I use the same notation. If you are not comfortable with the same notation, you can take in the case 3, multiplicity is r I've taken, you can take p also, then the formula will be n to the power p only. You can replace r by p also. Now it will be 2 to the power n to the power 2 because it is repeated twice. And in the multiply, there is only constant term is 1. Means constant term is 1, so we will take only q naught here. For constant, we will take constant q naught. So this will be the particular solution. And you can find the value of q naught after substituting in the given recurrence relation. In the next problem, the problem will look like this: fn plus 2 minus 4fn plus 1 plus 4fn equal to n square into 2 to the power n. Only we want to write the particular solution. Characteristic roots are 2 comma 2. Okay. So particular solution will be 2 to the power n. We will take outside, n square we will take outside. Now we will see this term. This is n square. So it is a polynomial of degree 2. So we will take all the term in the particular solution less than equal to 2 degree. So that will be q naught plus q1 n plus q2 n square. If it is 1, then we will go up to q naught plus q1 n. So this will be the way to assume the particular solution in the case of repeated root. So you all can solve this problem. Okay, in the next problem, you can repeat fn plus 2 minus 4fn plus 1 plus 4fn equal to n into 2 to the power n. Then your particular solution will be in the repeated root case. Case 3 I am going to discuss here. Case 3 is continue. So it will be n square because 2 times repeated, 2 to the power n. Now degree is 1, so we'll go up to q naught plus q1 n. So this is the ending of recurrence relation using the method of undetermined coefficient. In the next method, we will see another technique to solve a recurrence relation, that is called generating function method. And jet transformation method we have already studied in unit 2. So wait for third lecture on recurrence relation.